Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we'll continue more on applications of G versus X plots. This will be the contents today. What is internal equilibrium and internal process and a driving force or driving factor for a process, and in calfed tools such as thermocalc, what kind of driving force is used, and T-nut curve. Right. Now consider this binary single phase equilibrium. It's a AB binary alloy at temperature T2. Okay. Now this is a furnace now at temperature T2, and inside that we have this material. It's a AB alloy, and this is the composition of the alloy. It's a A-rich composition, something like 0.25B, 0.75A composition. And here we have this material existing in phi phase, and you can see why based on the Gibbs energy versus composition plots at this temperature. For this composition we see that this phi phase has the lowest Gibbs energy, and if you draw a tangent to this point you will see that there's nothing below that tangent. Therefore this phi phase will be the stable phase. That's what you see here. Now this is at T2. What if we go to a different temperature, T1? In that temperature, this is a furnace now. You see inside the furnace we have two phases, alpha and phi. Why? Because Gibbs energy versus composition plots are like this. They are intersecting, therefore there can be a common tangent, and this particular composition 0.25 mole fraction of B lies within this two phase region. So therefore its Gibbs energy is here, and two phases, alpha of this composition and phi of this composition, will be in equilibrium. Now, this is familiar to us. What is important to understand here is the process of achieving internal equilibrium. What we are talking about is at this composition, we bring this alloy from a high temperature to this temperature, right? High temperature in the sense temperature T2 to this T1 temperature, and you know two phases should become stable here. Therefore this is a metastable structure. Phi is not stable at this temperature, we know that, and this is the Gibbs energy of this phi phase at temperature T1, and obviously it is not the stable one we could sense. Now this is going to ultimately transform to this alpha plus phi structure, right? That is the stable state, and eventually Gibbs energy will drop here where the common tangent is, right? This is the stable state now. So in this process what has happened is an internal process within the material. Okay, within the material there is a change to achieve stable state from the metastable state. We are going to focus on this internal process today. So what happened is this binary AB alloy is moved from T2 to T1. Because of that it changes from metastable state to stable state, and diffusion of elements occurred into and out of each phase, isn't it? Think about it. Now you see the composition of phi, and it is having 0.25 composition overall. Now if it has to transform to this alpha and phi, you could see that alpha here has a very low B content and phi has a high B content. Therefore the amount of B has to decrease in this side of the sample and increase in this side of the sample. What does it mean? Two phases have to form, and interdiffusion of elements take place between these two volumes, and that is why you get a B rich composition here and a rich composition here. So both A and B elements interdiffuse to achieve this sort of phase formation. So each phase is now considered an open system, meaning they allow exchange of matter. So each phase, we are not talking about the overall system here. Now there are two phases. Each phase is now an open system. It can exchange matter and eventually reach the equilibrium composition. Okay, so that is where we call the material has achieved internal equilibrium. What is the driving factor behind this? Internal equilibrium and what drives it? Binary AB alloy moved from T2 to T1. At time t equals 0, we have this 5 phase which is metastable. After equilibration time, let's say some time t1, we get 5 plus alpha, which is the stable state. These processes happen internal process. What is an internal process? This is how it is defined. It is an irreversible process. It happens within the system to move it from metastable to stable state, achieving internal equilibrium. Okay, it is an irreversible process within the system. This is important. Okay, it happens within the system, so we put this word internal, and it is irreversible. You see, we bring it from some other high temperature to a low temperature, right? So entire transformation happens at low temperature. Definitely there is something which is highly metastable turns to stable state. So this is some kind of a abrupt process. This is not a reversible kind of a extreme slow process. Okay, so you are not reducing the temperature from T2 to T1 in an extreme gradual manner or things like that. It is just like that taken to another temperature. It's almost like rapid cooling sort of scenario. It is definitely not reversible. So it is an irreversible process. What drives it? Basically the Gibbs energy reduction. You see, Gibbs energy, if we plot it as an axis, metastable state initial state Gibbs energy is somewhere here, and the stable final state Gibbs energy is somewhere here. The difference in Gibbs energy, final minus initial, which will be a negative value, that is the delta G, which drives this transformation. So driving factor is decrease in Gibbs energy. It is the difference between the G values of stable and metastable phases, that is delta G. How do we mathematically calculate it? We put G of stable state first, which is the final state, minus G of metastable state, which is the initial state. We use the word driving factor here, but which is a more correct term, I feel, because in almost all the books this term driving force is used. That's a commonly used name. Okay, the force here is only a metaphor. It's not a real force. Okay, and hence it may be misleading. But we'll be forced to use the word driving force because the thermocalc software that we are going to use in this course also uses the same term. The same driving force we can understand in a different way as entropy increment. Okay, so metastable state, that's the initial state, final state as a higher entropy. The difference between them is the entropy change in the entire process. Of course, we are talking about the entropy change of the universe. We know it is a irreversible process, therefore definitely there will be an entropy increment. Recall Joule expansion, where we had an irreversible process, a gas expanding into a vacuum, and it's an internal process. Only the system undergoes a change and entropy maximization occurs there, and no entropy transfer happens. There is no heat coming in or going out. So whatever entropy change happened in that process is the produced entropy. So in any internal process, because we are saying it is irreversible, entropy production occurs to the maximum possible extent. This is going to help us understand a few things. Now we said internal process is irreversible, therefore it produces entropy. We are going to call it as the change in entropy in the internal process, and it's going to be greater than 0. Entropy change of the system is equal to entropy transferred, if at all there is any, plus entropy produced. We know that. And here we are talking about the entropy produced when we talk about the entropy change in the internal process. Now consider this new parameter psi. It is, let's say it is a measure of the progress of the internal process, meaning a state property such as the volume transformed. For example, if you think about a process happening, a product phase has to form, right? The product phase has some sort of final volume to be achieved. So if the process happens, the volume transformed is this psi. If that is the case, we can plot psi in x-axis. This is the progress of reaction. Let's say amount of product formed is in this axis, and the entropy change of this internal process in the y-axis. If we plot it like that, we'll get a graph like this. This entropy produced is a function of psi. Therefore, a change in this entropy is a function of psi, and reaction stops when this entropy reaches maximum, meaning this dips by d psi when it reaches 0, which is this maximum point, that is where the process stops. That's where this entropy reaches maximum. That is this state. Equilibrium value of psi, meaning if what all we consider the volume transformed for the product, whatever is the equilibrium volume to be achieved. If that is achieved, then it reaches the stable state. If at all any more volume of the product is formed, that is not stable. Okay. So stable state is somewhere here. That is where entropy produced will be maximum. Okay. As psi reaches a maximum value, the driving factor for the change gets over. Okay. This is in a way understanding the internal process and to what extent it will happen based on the entropy produced. Okay. This is the driving factor now. Okay. This is one of the ways to understand the driving factor. But of course, in the textbooks, mostly the Gibbs energy change will be directly used as the driving factor. But it is important to understand these changes based on this entropy produced as the driving force. This is going to help us a lot in getting some insights into the internal processes like this. And what is this entropy produced can be an even more intriguing question, and we can get into that later. Right. So about this, you can refer to this book. It gives a lot of information about what is this entropy produced and how it drives the transformations. So we said as psi reaches a maximum value, the driving factor for the change gets over. And based on this parameter d is formulated. D is equal to t dips by d psi. Okay, the t is multiplied with the slope of this. This can be a new state property. It is defined as affinity by the proposer. It can be shown that integration of d psi is equal to minus delta g. Minus delta g is nothing but the reverse of the driving force that we have been talking about. This minus delta g is called the integrated driving force or driving force, okay, by Hillert, and this is treated as a positive number now. Meaning we are talking about g of metastable initial state minus g of stable state final. Okay, the reverse of it, basically to give a positive number for any change to happen if there is a driving force. If the final state has the lower Gibbs energy, then this delta g, if it is a positive number, it is good to say that since there is a positive number for it to go from here to there, it will go. Right. So in that way, this is formulated as initial state Gibbs energy minus final state Gibbs energy. And the same thing is used in software such as thermocalc. Okay, they also use this minus delta g as the driving force, and they put one more layer to this, that is dividing it by RT. Therefore, it looks like a dimensionless number. If that number is positive, the phase transformation will happen. That is how the driving force is formulated in these tools. Of course, we will spend time sitting and calculating these driving forces and all in one of the future classes. I'm giving one example here, driving force in CalFET tool. We'll see about this when we do the training. For example, iron chromium system, if you consider, this is the phase diagram. Let's say at this temperature, 500 Kelvin, we are going to have a Gibbs energy composition plot like this. What does it say? It's going to say there are this alpha 1, alpha 2, two phases in this region. So you can see alpha here. So this side alpha, this side alpha. So two alpha phases will be there in this, meaning both are BCC with different chemical compositions. And that's what you see in the G versus X plot also. There are these three solid phases, gamma, alpha and sigma. The curves are drawn here. Gibbs energy versus composition plots are here. And you can see for alpha phase, the lowest Gibbs energy occurs when this common tangent touches it at both the ends like this. Right. So how to understand the driving force here? The difference between the G values of metastable and stable phases. Okay, for example, in iron chromium system, two BCC phases are stable at 500 Kelvin. We saw that. The metastable phases are sigma and FCC. So if at all at 500 Kelvin, you see sigma or FCC, obviously it is metastable. Okay. And this delta G is often normalized with RT, as I told in the previous slide, and represented as a dimensionless number. Okay. So here, if at all this sigma phase, okay, sigma phase of this composition, let's say this is our 60% is our composition. If we get sigma phase at 500 Kelvin, that is not going to be stable, right? And it is eventually going to change to two BCC phases of these compositions and the difference between this Gibbs energy to this Gibbs energy, that is the minus delta G for sigma, meaning sigma to transform to two BCC phases, that is the driving force. Similarly, if we have, let's say, 10% as our overall composition and FCC is the phase currently present, that is definitely going to be metastable and it will eventually transform to two BCC phases. I am basically talking about you are being in FCC state at high temperature and bring it to 500 Kelvin, allow it to transform to stable phases. But when you bring it at the initial moment, it is going to be there and it is not going to transform immediately. Therefore, it is called as metastable state at that temperature. At 500 Kelvin, it is metastable state. How much is the driving force for it to change to the two BCC phases? That's what we are talking about here. Right? Now, test your understanding with this example. Let's say case 1 is quite interesting. Two BCC phases indicated by the common tangent in BCC phase GX plot are present in the alloy. Meaning you put a common tangent here. This is present. What phases it indicates, this BCC and this BCC, they are present in the alloy. Okay. Now what is the driving force for it to go to equilibrium state? Maybe little confusing, but think about it. This question is intentionally asked like this. Second question is the phase sigma is stable at 500 Kelvin and 90% chromium, same temperature and composition. What is the driving force for it to go to equilibrium state? Now sigma is present. What is the driving force for it to go to equilibrium state? Think about that. Okay. Pause. Once you are ready with the answer, you can play and see the answers. Okay. For the first case, it is no brainer. You see, you already have this equilibrium state. What is the driving force for it to go to equilibrium state? That is the question. Okay, obviously, there is no other equilibrium state. So, driving force for it is actually 0, isn't it? So, why this question is asked is because if you want to identify what is equilibrium phase, there is a way to calculate for any phase what is the driving force to go to equilibrium state. If the driving force comes 0, in CalFAT software tools, you will see that. If the driving force for a phase comes to be 0, it means it is the stable phase. Okay. So that is how you identify stable phases in CalFAT tools. Now the second question is something that you can calculate where we have sigma phase as the stable phase. So now if you put at this composition a line like this, and this is the composition we are talking about, sigma phase composition. So is this sigma phase stable? Okay, obviously no. There is a driving force for it to change to this state. But this is where it will reach, meaning this is the final Gibbs energy where it will achieve two BCC phases. So this Gibbs energy value minus this Gibbs energy value is the driving force now. That is minus delta G sigma here. Right? So the answers are this: 0 for question number 1 and minus delta G sigma for the second one. Now let us look at this idea of driving force for transformation. Whatever we have seen till now is actually driving force for transformation, and it is slightly different from what is called as driving force for nucleation. So we will see the distinction now one by one. Consider there is a two-phase system, a solid solution and intermetallic phase. Both phases are there, and this is the intermetallic phase Gibbs energy curve. This is the solid solution Gibbs energy curve. Now this is our overall composition, and this is the initial state, meaning at this composition we somehow have one solid solution now. Now will it be stable? What it will eventually transform to? It will transform to this state. Okay, from this Gibbs energy it will fall to this Gibbs energy, and these two phases, solid solution and intermetallic, will come in equilibrium. That is going to be the final state. So this is a 70% B fully in single phase solid solution form to start with, and it is going to go to this equilibrium state where a two-phase equilibria of solid solution plus intermetallic will form. So what happens here is this Gibbs energy decreases to this Gibbs energy now. Now this entire Gibbs energy change that we have been seeing till now, we called it driving force, but that is driving force for the entire transformation. So this is driving force for the transformation, where the Gibbs energy of this metastable state and Gibbs energy of the final state are taken, and the difference between them is calculated to be the driving force. It is different from what is driving force for nucleation. We'll see what is this. So we know for sure when this solid solution is there, it is going to eventually transform into solid solution plus intermetallic. So if that intermetallic has to form, it has to nucleate and grow. Okay, there is this process of nucleation and growth. If we talk about kinetics of phase transformation or mechanism of phase transformations, we'll be seeing those ideas. Okay, since we are dealing only with thermodynamics till now, at least in this class, we haven't seen about such ideas. But let me tell you that if at all there is a phase to form from another phase, it has to nucleate and grow. So this nucleation and growth is there in most of the transformations. There are certain exceptions to that, but this nucleation becomes quite important, and it also requires a driving force. So we'll now see what is the driving force for nucleation. To understand that, we have to draw a tangent like this to this solid solution itself. Okay, this is our initial state. Draw a tangent to that like this, and then draw a parallel line to that and make it a tangent to this intermetallic phase Gibbs energy curve. Once it is done, see the distance between them from here to here. Of course, this length you can measure anywhere. You can measure here also. These are just parallel lines. So I am putting it here to show that it touches here. It need not touch the bottom. Okay, it can touch anywhere. This curve is quite the curvature here is quite sharp. That is why you are seeing it as if it is touching in the bottom. But if this is a shallow curve, it need not touch in the bottom. It can touch anywhere else. So the distance between these two is the driving force for nucleation. Right. So let us take this away here. This is driving force for nucleation. Beginning of the transformation has a different driving force compared to the overall driving force for the transformation. Beginning in the sense the nucleation we are talking about. For nucleation, there is a different driving force. So this is an important distinction to keep in mind. So what procedure we follow to get this? Draw the tangent to the metastable state G. The metastable state in this case is single phase solid solution, and then draw a parallel to it and make it a tangent to the product phase Gx plot. So this is going to be the product phase now, the intermetallic phase. The Gx plot of that is now having a tangent which is parallel to this line. Then measure the distance from the parent to product, meaning from here to here. That's how we calculate driving force for nucleation. So now we will look at what is T naught. This is another important idea to understand some of the phase transformations. This is a temperature T1 where we have two phases intersecting like this, and we take this composition to phase diagram and plot tie line information like this. We get the entire phase diagram by repeating this at multiple temperatures. You know that story. Now point is, look at this point here. This is where Gibbs energy of phi and Gibbs energy of alpha are equal, right? Both phases have same Gibbs energy here where they intersect. What about this composition? Take this composition and put it in the phase diagram against this temperature. Okay, it is somewhere in the middle of this alpha and phi composition points. The same thing if we repeat at multiple temperatures, we will get dots like this. If you join all of them, what you get is a T naught curve. At various temperatures, Gx curves are plotted, and the composition at which the Gibbs energies of the two phases are equal are traced on phase diagram like this. Okay, that is T naught curve. And this is important to understand certain phase transformations such as partitionless solidification, Martin-Stich transformation, massive transformation. We will see few examples of that also in future. Okay, we will stop with that. Thank you. I hope the lecture is useful. See you in the next class.